All right, so before I get going on talking about balancing of equations just a little bit more, any remaining questions regarding the homework that should be turned in by midnight tonight? I know that a few people have already turned it in, but you have until midnight to do it.
The all problems that we have to solve on homework, we have in our notes, right?
Yes.
Basically.
They all should be topics that were pretty well addressed in the notes.
All right, yeah, I did have, and another half has stuck on a couple of problems, so I'm still kind of trying to figure out.
Because we did things like grams and moles and atoms, we did empirical formulas, we did empirical converting over to molecular formulas, we did some percent by mass.
Did you load it, the videos on
This afternoon. I did it this afternoon because it took me a while for the YouTube thing to crunch through. So I uploaded them to YouTube today, and it took a few hours for them to crunch them, and they should now be available.
Okay, thank you.
Other questions?
I have a question that's not specifically the homework, but has to do with the homework.
Okay.
So I'm on this chapter 3 homework. We're dealing with like weighted percent, the weighted average again.
Yes.
And I was wondering, since we were tested on that on the first test, which was chapters 1 and 2, are we going to get tested on that again for the test for 3 and 4?
Okay, I haven't finished typing the test yet. I just started typing the test a couple of days ago.
Okay.
If I do put it on the test, it will probably be a single question.
Oh, okay. Cool.
Because it doesn't really exactly go away entirely. It's a really useful tool, so it also kind of sort of applies to a degree to some of the lab stuff we're doing. So yeah, it doesn't go away entirely. So I've only got about a quarter of the test typed in so far. I was actually working on it for a little while this afternoon. I will let you know more thoroughly next week after I've typed some more on it.
One more question.
But even if I do put it on the test, it'll probably be just one question.
One more question, sir. On our test, and question 22, it says a reproducible measurement is an accurate one. True or false? Reproducible means that it's repeatable, that we can repeat it again and again,
yes,
right?
But for instance, if I am like shooting at the dartboard with my darts and I hit the wall on the left-hand side 3 times in a row, that's reproducible, but it's not accurate.
Oh, I thought it's meaning like that we gain making the same result again and again and again.
Yes, but if you have faulty equipment, if you have faulty procedure, if you have a procedural error that is consistent, you can get the same wrong answer again and again and again, and it's not accurate. It's only reproducible.
Okay.
Okay, I have a really giant cat named Stormageddon. For instance, if I pick him up and I step on the scales, okay, granted, it will report the weight of me and the cat, but that's not accurate for my weight, and it's not accurate for his weight. But if I do it 3 times in a row, I have a reproducible error because I've done the same thing wrong 3 times in a row. It doesn't make it the right answer. It just makes it reproducible. This is actually a problem in lab. People will often make the same procedural error multiple times in a row without realizing it. So that's kind of why it is kind of a crossover topic between lecture and lab. Other questions? All right, I'm going to segue over to balancing reactions. I'm going to try to do this on my board here. So this one's not in your notes, but I figured I'd do one, try to do it this way. So I have calcium atoms and phosphoric acid, and I am making as my products calcium phosphate and hydrogen, which is probably in the gaseous form because it's an H2. So if I want to make this a balanced reaction, and like I said, it doesn't really matter where I start, but one of the things that's semi-obvious is my big giant molecule on the right-hand side there has 3 calciums in it. So I can't really have less than 3 calciums on the left-hand side. So let me do the next row down here. And kind of show you the beginning of the balancing part. All right, so I fixed one thing here. I fixed the fact that, okay, now actually my calciums match because I've got 3 on each side, but I've still got a couple of other things that don't match up the way they're supposed to. I could address my hydrogen problem because in my phosphoric acid, I have 3 atoms of hydrogen. But over on the right-hand side in my gas, they only come in 2s. So that brings me back to that kind of least common multiple issue. And one of the things I could do would be shoot for a way to get 6 hydrogens on both sides. So again, I'll kind of do a level of correction here. All right, so this is a partial correction. I put a big 2 out in front of my phosphoric acid. So that will give me now 6 hydrogens, but I still haven't corrected it on the right-hand side. So I need to do another little fluff here where I put a big 3 out in front of my hydrogen gas. This should hopefully give me a balanced reaction. 3 calciums each side. I've got 2 times the sub 3 for my hydrogen, but on the other side, I've got 3 times the subscript of 2. So that should give me 6 hydrogens on each side. Because of the big 2 out in front, I have 2 phosphates, PO4s, and I had a subscript of 2 for my phosphate over on the right-hand side. So that should make that match also. And again, I could have started with my hydrogens. I could have started with my phosphate issue. I happen to pick the calcium as like a starting place. There is no one hard and fast place that you have to start with. I know that there are textbooks that will sometimes give you ideas about like, start only with the things that are diatomic, or start only with the things that are metals. That's really not true. As long as you are careful and keep track of all your pieces, it doesn't really actually matter where you start. So questions about generalized balancing before I pull up my notes thing, which I fixed. Okay, I actually went back and corrected a whole bunch of errors in that, as far as like where it's displayed and some missing subscripts and things like that. So I did go back and fix that. All right, let me see about sharing my screen. All right. Like I said, I don't really, I have, there is no perfect textbook, okay? All textbooks have their pitfalls. One of the pitfalls of this particular textbook is it doesn't quite give you as much detail in some of the reaction descriptions as I would like. So this little bit here about the aqueous is one of the things it kind of glosses through. So we talked about aqueous a little bit. It got mentioned oh so briefly in chapter 1. It popped up again just a little bit when we mentioned acids for chapter 2. It comes back again now. Anything that's aqueous, Latin roots, means dissolved in water. We're all kind of familiar with water is 2 hydrogens and 1 oxygen. But you have to think about for a moment that it's not, I'll call it sequential. It's not HHO. The oxygen is actually in the center of the molecule. And I went and dug up this picture to cut and paste into here to make it a little bit more obvious. The other thing that is deceptive, and middle school textbooks are often guilty of this, a water molecule is not linear. It is not a straight across. Yes, I could type HOH on my keyboard and it makes them all look like they're in the same line. In reality, that is not true. Some words that we'll kind of hit on again in a later chapter, but you will see water referred to as being a bent molecule. You also might see it referred to as being a V-shaped molecule. Both are equally correct in terms of their description. If you kind of look at the labeling there in the picture, the bluish color that's up near the oxygen end is helping to indicate that because this is a not linear molecule, because it has kind of a pointy end to it, that the electrons that tend to spend more time with the oxygen than they spend with their hydrogen tends to make that point end of the molecule a bit more negative. This is why it says slight negative, because it's not an ionic bond. When we did nomenclature, a lot of the salts that we created were ionic because you took things that were literally a positive ion and literally a negative ion, and you allowed their opposites to attract each other to create a molecule. This is less true of water molecules because the bonding is not full-blown charges. Note that both hydrogens kind of poke in the same direction. In this case, in this picture, they're both pointing downward. So the lower half of the water molecule is kind of positive, and the upper half of the molecule is kind of negative. And again, words that are going to get a little bit introduced here that eventually will come back around again a second time later. This makes water polar because one end is a different charge from the other end. And because I'm a chemist and have a warped sense of humor, I'm always amused when you go in the grocery store and you go down the aisle with all the bottles of water and they go, polar water. And I'm like going, duh. I know that that's not what the branding is supposed to indicate, but it is in fact true. Water is polar. Another facet that makes this difference is there's kind of a sharing of electrons going on. Something we didn't really see when we were talking about the ionic compounds. They were all about stealing. if you have a water molecule and some of the molecular compounds, specifically things that are non-metals, they tend to do a level of sharing. Not necessarily equal sharing, but they do a level of sharing. Some more words that we kind of touched on in chapter 3 when we talked a little bit about solutions. Kind of hop back again here. We've got solvent, the thing you are dissolving stuff in. Especially in lab, what we do in lab, most of the time it tends to be liquid. Not always. It can be another liquid other than water. We also saw technically it can also be some other things too. Some of the atypical solutions. For solute, the thing you are dissolving. Usually it's a solid. Doesn't have to be. But for when we are making solutions in lab, it often is. Another thing we kind of mentioned at the end of the last chapter that pops up again here. Polyatomic ions don't fall apart in water. You can make them fall apart. There are ways to do it. Usually they involve such things like heat and or acids. But under normal circumstances, they stay stuck together. So I gave you 3 examples here. We've got sodium chloride, obviously table salt. It's an ionic compound. When you drop it in water, the sodium swims away from the chloride, and they actually become 2 separate items in your solution. Here's one that's deceptive next, because people are very tempted to make their Br2s stick together. This molecule actually kind of resembles a water molecule. You would have the magnesium atom in the center, and one leg would be a bromine, and the other leg would be a bromine, such that when you drop them in water, you actually have 3 separate pieces, okay? You have the cation, which is your magnesium, but you have 2 separate, they are not stuck together, bromides. So 3 pieces there. Similar and also dissimilar is the last one there. Calcium would be in the middle. Calcium we have seen as an alkaline earth metal. NO3 is nitrate. The nitrates will not stick to each other. Now, the nitrate itself will not fall apart. You won't get separate ends swimming away from your 3 O's. The NO3 will actually stay together in water. Like I said, there are ways to make this not do that, but for the moment, things that are polyatomic, we will assume will stay stuck together if you have an aqueous solution. So we're heading in the direction of types of reactions. We're going to look at 4 big categories: precipitation, acid-base, gas generating, and oxidation reduction, which often goes by the shorthand name of redox. When I was in lab on campus on Monday, I filmed the rest of the reactions and have now loaded them, for those of you who have me for lab, to the lab shell, because the next dry lab after this rotation is done, because this rotation is the nomenclature lab combined with the separation of a mixture lab, half of you have probably done the separation lab now, and half of you will do it next week. But then the next rotation of labs involves the metathesis reactions, which is a combination. It's 11 reactions that encompass kind of 3 out of these 4 categories. There is not a redox reaction as part of that dry lab, but there is precipitation and acid base and gas generating. So what I did was, in addition to taking a batch of still pictures, I also took a bunch of little, they're roughly 1.5 minute videos where I tried to zoom in close and just show my hand in the test tube and the labels, and show you each of the 11 reactions happening so that you can watch them and record observations when you get around to doing that lab. So this is, again, a little bit of a crossover between lecture and lab, in that things we're going to talk here about in chapter 4 are part of that dry lab, because we can't do all of them for real. Believe me, I think it's really kind of cool to watch them happen. And the best I could do was actually give you little videos as opposed to just stills. That way you can actually kind of watch it happen. So we're going to work on the precipitation ones first. Precipitation reactions involve mixing 2 solutions. Our first solution for this beginning example is magnesium chloride. Note there are 2 atoms of chlorine attached to my magnesium. To this, I am mixing some silver nitrate. Here we have a polyatomic. So one of the things that you have to do as kind of your starting point is to think about the fact that these particular reactions are going to, or reactants rather, are going to split apart. Your magnesium chloride, just like I was sort of talking about above there, is going to split into 3 pieces, because the Cls are not a polyatomic. They are just individual items. My silver nitrate, though, because it has a polyatomic involved, is going to split apart in 2 big chunks. We've got the silver ion, and then we've got the nitrate chunk. So in algebra, there is that thing that has to do with doing factoring, where you do FOIL, first, inner, outer, last. And the idea actually kind of sort of applies here. And since I don't have a chalkboard to write this on. So here we've got the MgCl2 and the silver nitrate. So first and last, your magnesium will try to stick to your nitrate, because the magnesium is the first one and the nitrate is the last one. The silver will try to stick to the chloride. Now you can't do it the other way. You can't stick magnesium to silver because they're both positive. So it doesn't work. You can't stick chlorine or chloride to nitrate because they're both negative. We also have to obey the rules that we started learning when we did nomenclature of, when you write these out, the positive one has to be in the front. So you can't do CLAG. It has to be AgCl as a, well, we might have made this. And the other one, you have to put the magnesium out in front and the nitrates at the right-hand end.
So it's NO3 have 1 charge and it's going to turn to...
Yes. NO3s, we learned back in nomenclature, are a polyatomic named nitrate that has a -1 charge on it.
So it's not going to separate to nitrate and oxide.
Right, right. The N's are not going to fall off from the O's. That is true. Now, I have a beaker full. Even though I'm adding these two things together and it kind of looks like, where did my second nitrate come from? The idea is, since you have a beaker full, which means you have millions of little ions swimming around together, you can use as many as you need to make neutral molecules. Because that's one of the rules we don't want to violate this semester. We don't want to violate the idea of when you get to the end and you have a molecule, it better be neutral, okay? So I need 2 nitrates to match up with the fact that my Mg has a +2 charge on it. So my 2 options were, well, okay, if I did this for real, if I put my stuff together in my test tubes, I would see that I had a white precipitate. It would get cloudy to start with, and if I let it sit in the test tube for a little while, it would actually begin to settle to the bottom of the test tube and make it look sort of like a wet, powdery gunk at the bottom of the test tube. That's actually what your precipitate is. So the other piece to this puzzle is, well, okay, I possibly made silver chloride, or I possibly made magnesium nitrate. Well, which one is it? There are rules. So now we begin to get into the rules. The rules, and later I'll go through all the rules together. One of the big rules is most nitrates are soluble. Now, the word soluble means they're not going to stay stuck together. It's kind of like bumper cars. They might hit each other. The magnesium might touch the nitrates, but they're not going to stay stuck. There's no Velcro, okay? They kind of bounce off each other and keep on going. But there's another rule that says most chlorides are soluble except silver, lead, and mercury. So I saw a precipitate and I had 2 options. My options were it might have been silver chloride or it might have been magnesium nitrate. And I'm using the rules to decide. One of the rules allows me to kind of go, well, yeah, it's not that one, okay? But by knowing that nitrates are soluble, I can go, well, okay, it can't be that one. But then I'm using the other rule as kind of a confirmation. Yes, I did get a precipitate. I did see it. And according to the rules, it actually is predictable. Silver and chloride stick together and are not soluble. So silver chloride is the identity of my precipitate. And I have a couple more so we can kind of develop kind of a pattern for this. Sodium sulfate and lead nitrate. This time around, I've actually got 2 different polyatomics. My sodiums, both of them, will fall apart, fall off of the sulfate. So I'll actually have 3 chunks floating around. 2 of them are sodiums and 1 of them is a sulfate, SO4, -2. My lead happens to be the +2 version of lead, and it falls away from the nitrates. The nitrates do not stay stuck to each other. So I have sodiums, I have sulfates, I have leads, lead 2s, and I have nitrates. Back to the first and last and third and second idea. If I stick my sodium to the last chunk of my option, because it has to be the other thing that's negative, one of my possibilities would be sodium nitrate. And since sodium is a +1 and nitrate is a -1, one of each will give me a neutral molecule. And then I do third and second. My Pb +2 will try to stick to my sulfate -2. Make sure you are writing the metal at the front of the molecule. So now I have two options, and I go back to the idea of, okay, which one is my precipitate? So sodium sulfate and lead nitrate will give you a kind of gray-white precipitate in your test tube. How do I figure out which one it is?
What if it would be impossible to make it neutral? What then is going to be?
There are no impossibilities in precipitation. You use as many pieces as you need to construct a neutral molecule. That's why it says balancing comes in a few minutes. Right at the moment, we're creating molecules and we're not balancing reactions. Balancing is a coming up step. One problem at a time. First, we have to create a neutral molecule. Then we'll go back and worry about the balancing part. So here's your solubility rules. This is not exactly the way that they are stated in your textbook. I like this version better. This actually came from a different textbook. So they're also kind of sort of in order of importance. Basically, by the time you work your way through rules 1, 2, and 3, using rules 4, 5, and 6 are kind of almost confirmation. So if I look at these rules and it says most nitrates are soluble, and I go back up an inch and go, okay, I had these two options. Was it PbSO4 that made my precipitate, or was it NaNO3? Well, it can't be the NaNO3 because nitrates don't make precipitates. So I can kind of go, yeah, okay, not NaNO3. On the other hand, it's helpful to have a confirmation rule. So if you kind of skim down to rule number 4, it says most sulfates are soluble except barium, lead, and calcium. And ding, 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 my PbSO4 is a notable exception. So this is my confirmation. My PbSO4 has to be my precipitate. Looking back at some of the other rules there, anything that starts with a sodium, a potassium, or an ammonium, NH4+, are soluble. So even if I didn't use the nitrate rule to get rid of my NaNO3, if I looked the next rule down, it's still not going to give me a solid because there's a sodium present. The chloride rule, anything else with chloride is going to be soluble, not silver, not lead, not mercury. Mercury 1, remember mercury 1 is weird because it's the one that travels with a buddy. Sulfate only has 3 exceptions. The bottom 2 rules are stated kind of backwards from the other ones. Note that it says in number 5, most hydroxides are not soluble except sodium, potassium, and calcium. So that means anything else with a hydroxide. You could have lead hydroxide. You could have iron hydroxide. Those would be solids. They would be not soluble. But the sodium and potassium, you could almost go C above, okay? You already knew things with sodium and potassium were soluble based on rule number 2. Calcium is the only kind of variant there. And then sulfides, carbonates, phosphates, and chromates are not soluble, except C above. unless they're stuck to sodium, potassium, or ammonium. So like I said, the rules are kind of in order of importance. You can eliminate an awful lot of possibilities with the first 3 rules. And then the bottom 3 rules are kind of about confirmation. So let me pick on another one here. Iron sulfate and sodium nitrate. Does it precipitate? And if so, what did it make? That's what ID means. Again, we've got some polyatomics going on here. The SO4 is not going to fall apart, and the NO3 will not fall apart. First and last. Oh. And I realized I have a goof. I have FeSO4 and my subscript is wrong. It's supposed to be FeNO3 2 because it's, okay, since iron is stuck to sulfate, it has to be the +2 version, and you don't get to change charges on your metals mid-precipitation. I realized I just put the wrong subscript on my NO3 there. It should be FeNO3 2. Still doesn't really change the end result, though. Nothing happens. You might see a color change. Iron sulfate has kind of a yellowish tint to it because of the iron. Sodium nitrate is clear and colorless. If I dump them together, nothing happens. You will see this roughly 15 to 20% of the time. If you pour 2 aqueous solutions together, occasionally, nothing happens. And in fact, that metathesis lab that I just finished loading all the videos to, one of those 11 reactions does nothing. Now, why? Okay. Because if you look at the nitrate part of your iron nitrate, okay, all nitrates are soluble, so it can't be FeNO3, even if though I put the wrong subscript on it. FeNO3 3 or FeNO3 2, still soluble. The other one starts with sodium. Things with sodium are soluble. So even though they tried to swap, they didn't do anything. So sometimes you will get no precipitate. And note my explanation, though, for the option. This semester, okay, first semester chem, we are going to pretend that you could never get 2 precipitates. In fact, it is actually a possibility, but it is a possibility that is not dealt with until second semester, because we need another skill set in addition to the things that you learn this semester in order to be able to deal with those possibilities. The topic is known as KSPs and differential precipitation. But for this semester, your options are you made no precipitate, which happens occasionally, or you made 1 precipitate, which happens most of the time. We're going to ignore that possibility of both of them precipitated. All right. So we've been talking about the swapping. First and last, third and second. So it's not exactly foil, but it's kind of sort of like foil. Now we got to start writing some equations. Now we're actually going to worry about how many as well as balancing. So there are 3 different types of equations for precipitation reactions, and also that kind of sort of bleeds over into gas generating and acid base also. Not so much for the redox ones. first kind is called a molecular. Then there's a second kind referred to as a complete ionic equation. And then there's a third one known as a net ionic. In the grand broad strokes scheme of things, I will say the first and the third one, the molecular and the net ionic, are somewhat more important than the complete ionic. That doesn't make the complete ionic unimportant, but I will call it somewhat less important. You can do things with number 1 and 3 that you don't need number 2 to complete. All right. So one of the things that a molecular does for you is it tells you a little bit of everything. Shows you all the products, shows you all the reactants, gives you indication by means of things like AQs and S's as to what stayed stuck together and what didn't stay stuck together. So here's my example. I've got iron 3 chloride, FeCl3. Since it's a reactant and it's aqueous, we know that it's going to fall apart when we dump it in the test tube. I've got some sodium hydroxide. It's also aqueous, which means the sodium is going to fall off from the OH part, because hydroxide is a polyatomic. It's a small polyatomic, but it is a polyatomic. Since my iron is the +3 version, and the way I know that is because on the left-hand side, it was stuck to 3 chlorines. And as I said, in the course of doing precipitation reactions, you don't get to change charges on your transition metals. Whatever you started with, you're kind of stuck with. So since my OHs are -1s, when I create a molecule out of the first and the last, the Fe and the OH part, in order to make this be a neutral molecule, it's got to be FeOH3. I got to have 3 hydroxides. Now, I know it is extremely tempting to write Na3Cl3. People do that all the time. That doesn't make it right. A sodium that has a +1 charge sticks to a chlorine with a -1 charge. But you get 3 chunks. You get 3 NaCls. The only thing that has duplicated subscripts are peroxides and mercury, because mercury's weird no matter how you deal with it. So this one's balanced. If I go back and kind of look at it, I can go, okay, 1 iron on each side. That's cool. The 3 Cls that started out their journey with the iron are now living with the sodiums, because I've got 3 sodium chloride molecules. My 3 sodiums that started out life stuck to hydroxides are part of the sodium chloride molecules. And those 3 OHs became part of the iron 3 hydroxide molecule. So first you write the formulas for the molecules, and then you go back and add your subscripts as needed. If I had written this in steps, and perhaps maybe I should have shown that, because I'm, like I said, I'm still trying to adjust the fact that I can't write stuff all over the board and draw arrows and bells and whistles and all that. In my initial phase, I probably wouldn't have had the 3 written in front of my sodium hydroxide or the 3 written in front of my sodium chloride. I would have first constructed the molecules and then gone back to balance it. So complete ionics look messier. Every molecule that was aqueous falls apart and is shown as falling apart. So my FeCl3, and remember your Cl3 doesn't stay all stuck together, they're actually 3 separate little bits. So I have an iron plus 3 and 3 chlorides. My 3 sodiums fall apart from my 3 hydroxides. But note, the one and only thing that was not aqueous doesn't fall apart. And that's kind of the whole purpose. It's my precipitate, so it doesn't fall back into ions. It stays glued together. But my sodium falls apart from my chloride. So I have 3 NAs and 3 Cl minuses. Complete ionics are longer to write because you end up having to show all your charges. You always are looking to see which thing did not fall apart. In this case, it was the iron hydroxide. And we're actually going to give a name to the things that look the same on both sides. So now that football has started again, yay! Even though there's no spectators in the stadiums, okay, because the spectators are the people who usually sit in the stands and watch. We're all sitting at home and watching stuff on our TVs. So we are still spectators because we are not involved in the game. We are not down on the field playing. And that's why you often have ions who are called spectators. So in this case, if you look at the sodium, and over on the left-hand side, it's just got a plus with it. And I look over on the right-hand side and, oh, it's also got a plus with it. It didn't do anything. It just floated around the beaker and watched. So did my chloride. My chlorides were just minus on the left-hand side. And they're just Cl minus on the right-hand side. They didn't change. So spectator ions are a thing that are visible in your complete ionic reaction. Now, if you make them go away, if you delete your spectators and only write what's left, you get a net ionic equation. So when you get your paycheck, top of your paycheck, and you look at the stub, okay, the top of your stub says gross pay. Down to the bottom of your stub, it says net pay. And due to federal taxes and state taxes and whether or not you pay insurance out of your paycheck and FICA and a whole bunch of other stuff, your net is always less than your gross. And the same thing is true here. My molecular equation kind of showed me the most stuff. Complete ionics showed me more, but in a slightly messier way. And then if we get rid of all the spectators, we get down to what's left. And all the net ionics for precipitation reactions kind of have a pattern. We see here positive thing plus negative thing, arrow, neutral molecule. And they all kind of behave that way for the net ionics. So in this case, the positive thing happened to be an iron plus 3. The negative bits are my OH minuses. And then I stuck them together and I made a nice neutral molecule out of them. my FeOH3, iron 3 hydroxide. And so that's kind of my pattern, okay? You see cations plus anions, then you're going to see your arrow, and then you're going to have the neutral molecules on the right-hand side. So let me look at another example here. If I take calcium chloride and potassium sulfate, okay, so I need to first and last, my Ca will try to stick to my calcium sulfate. My Ks, my third thing, will try to stick to my second thing, because remember, you got to put the positive bits out in front. You can't write ClK. It has to be KCl. And it also can't be K2Cl2. You have to pull the 2 out in front and make it into a subscript. Not subscript, coefficient. So 2 KCl's. If I look these up, if I looked up calcium sulfate, okay, there's a rule for sulfates. It says most sulfates are soluble, but barium, lead, and calcium. So ding, ding, ding. My calcium is my precipitate. I could use 2 different rules to decide against my KCl. I could use the rule that says most chlorides are soluble because it's not silver, lead, or mercury. Or I could use the other rule that says most sodium, potassium, or ammonium are soluble. Either way, KCl is not going to give you a precipitate. So molecular showed me everything, and I balanced it by putting a 2 out in front of my KCl. Then for the next layer, so everything that was aqueous, everything that fell apart, everything that was not a precipitate, I split into its pieces. So I've got some calcium ions. I've got a couple of chloride ions. Note, my 2 Cl's do not stay stuck to each other. Same thing is true with my K's. They do not stay stuck to each other. The 2 comes out in front. And I have a sulfate. So because it's a complete ionic, basically everything on the left-hand side fell apart because they were all aqueous. My calcium sulfate is the one and only thing that stays stuck together because it made your solid. And then I split my Ks and my Cls back apart again, 2 K pluses and 2 Cl minuses. Once I delete my spectators, my Ks are spectators and my Cls are spectators. Because if you compare the left-hand side of the arrow in the complete ionic to the right-hand side of the complete ionic, they didn't change. They look the same on both sides. So my leftovers are the calcium ion plus the sulfate ion makes calcium sulfate. See your pattern then? We've got positive thing plus negative thing gives you neutral molecule. Like I said, there's a pattern to this. Now, we did say that since sometimes you have no precipitate, if there's no precipitate, there is no net ionic because there's nothing left over that didn't get canceled out. If I had added KNO3 and sodium chloride, okay, my potential options are sodium nitrate and KCl, but all sodiums are soluble, all sodium ion containing molecules are soluble, so it can't be sodium nitrate. All chlorides are soluble, but so are all things that contain the Ks, so it can't be the KCl. Even though I can write a molecular, I could technically write a complete ionic, but there's nothing left over to write a net ionic. Nothing doesn't cancel out. This does occasionally happen. Be aware of that. So one last example tonight. This one kind of goes through all of it together there. We've got silver nitrate and ammonium carbonate. First and last gives me silver carbonate. Second and third, actually I said that backwards, third and second gives me ammonium nitrate. Remember, don't leave your twos there. The two's got to come out in front. So my molecular one, in order to be fully balanced, I need a 2 out in front of the silver nitrate. I need a 2 in front of the ammonium nitrate. So the 2's are there to make it balanced. Everything that was AQ, I split. So I get 2 silvers, 2 nitrates, 2 ammoniums, and 1 carbonate. On the right-hand side, do not split your silver carbonate, but do split your ammonium nitrate because it had an AQ next to it. So I get 2 NH4s and 2 NO3s. Then I'm going to go back and ditch the NH4s and the NO3s and figure out what's left over. I have silvers left. I have a carbonate left. So there's my pattern, positive thing plus negative thing. Stick them together, make a molecule, make a neutral molecule, and that will give you Ag2CO3. Looking for the patterns as well as paying attention to your charges is a really key function here. And that's about as far as we're going to go tonight. But keep in mind, it's like things you learned in the nomenclature chapter, all those polyatomics, okay? Remember I said they don't go away, okay? We're not really actively naming them, but we are still using them, realizing that they don't fall apart, and realizing that each of those polyatomics has their own charge to them. And the charge is a really key portion of being able to figure out how many pieces do I need to make a neutral molecule. There's patterns behind this. Learning the fact that things need to look kind of certain ways. Like I said, peroxides are rare. And except for Hg2Cl2, you're pretty much never going to see 2 subscripted 2s in a row. I know it's tempting, and it's a really common habit that people make wrong. They write things like K2Cl2. You got to pull the 2s out in front. You got to turn them into a coefficient. When you write your equations, you're finishing equations, and then you're balancing them. It has to be done in kind of 2 steps. When you're doing algebra, a lot of times you rearrange things, and then you go back and multiply the appropriate things together. Things like, what do they call that? Distributive property. If you have A plus, in parentheses, B times C, you can, or B plus C rather, you can split it apart and you can go, okay, A times C plus B times C. That's kind of the idea we're using here. You're putting things in different groups in order to make sure that they're neutral. So there are extra rules that are not algebra rules exactly. Chemistry has charge rules. We're a little more than halfway through the chapter at this point. We might finish the chapter on Tuesday, but probably not. It's probably going to take us into next Thursday to finish up the tail end of chapter 4. However, remember, homework for chapter 3 is due tonight. Fun things I get to do with my weekend. Great homework. All the homework is already loaded except for the very last one of the semester, which I have to fluff before I put that up. But all the other ones are loaded. Chapter 4 homework is actually available if you want to look at it over the weekend. But it won't be due till at least a week from now because we've got a ways to go. Questions? I know, it's a lot of information. Doing precipitation reactions and doing balancing is a lot of data that kind of has to crunch. Questions about homework that's due tonight?
Yeah, I do. It's on number 6. You ask how many grams does 0.25 moles of CuCN weigh? So for there, the first step, would you find the individual weight of each molecule, or do you just go ahead and multiply 0.25 times the 10 times or whatever that number is for moles?
No, since it asks you about the moles, you're going to have to do a molar mass. If you have a molecule, you need to look up the atoms on the periodic table and figure out how much 1 mole of that molecule will weigh, and then you can multiply by the part of a mole you're using.
So we like summarize copper, nitrogen, and carbon, right?
Yes, so you have to look up those 3 atoms.
From periodic table, and then summarize them, and then multiply by 0.25.
Yes,
Okay.
and note that since it says copper cyanide, it's
Copper.
is it CuCN or is it CuCN2?
CuCN.
CuCN.
So if it's CuCN, so 1 atom of copper, 1 atom of carbon, 1 atom of nitrogen. Add them all up. I'll add up all your periodic table weights. Then you can go ahead and you do your multiply by your 1/4 mole.
Okay.
Do it in 2 steps.
All right.
Other questions?
I have a question, but it's actually not on the homework itself. It's actually on Dry Lab 2.
Okay.
Can I ask that? Okay.
Yeah, sure.
I keep getting myself all confused. It's on the last part. So part C, number 6, letter R. It tells us to write the formula for the following compounds, and letter R is calcium hypochlorite.
Okay.
And every time I start going through that, I start overthinking it and then confuse myself.
So hypochlorite is a polyatomic. When you look up hypochlorite, either in your textbook or in your lab book, because there's a really decent table of polyatomics in your lab book, hypochlorite is OCl minus.
See, I've got perchlorate. Am I really
has
just not seeing it?
4 oxygens, so it's ClO4, but because it has hypo, that means there's a single oxygen. It should be in the group of -1 charged. Actually, that sounds weird. They have a -1 charge. There is a group of -1 charged ions. Your textbook groups them by charges rather than grouping them by names.
Oh, okay, I found it. I apologize. That will make it a whole lot easier.
Yeah, the way they organized it is different than the way the textbook organizes it.
Oh, definitely. Okay, thank you. I'm sorry.
Okay,
I could
that's
not
fine.
find it.
Other questions? Otherwise, turn in homework before midnight, and I will spend part of my weekend grading homework, and we will talk about homework on Tuesday and dig deeper into precipitation and upcoming reactions.
Sounds
All right,
good. Thank you.
I will see you next week then.
Bye.
All right, bye.